Alrighty, we have a doozy of a problem here. It's number 33 in section 3.6. That's on page 359. The instructions are sketch the graph of the function using the curve sketching guidelines on page 348. That's a 10-step plan. No, I guess I should read the problem here out loud. F of x equals e to the x minus e to the negative x over 2. So, let's go ahead and write the problem down again. F of x equals e to the x minus e to the negative x over 2. We might even write that 2 out in front if we take a lot of derivatives and write it's 1/2 times those things. First off, what's the domain? Well, the domain works pretty well here. I can put anything into an e to the x. I can put anything into an e to the negative x. I always get an output. There's no place the denominator will be 0, so everything's in my domain. That's fairly convenient. How about X-Intercepts? Well, X-Intercepts are where this would be 0. So e to the x plus or minus e to the negative x over 2. I'll multiply both sides by 2. Well, that's sort of convenient. That gives me 0 equals e to the x minus e to the negative x. Well, that's really just saying that e to the x equals e to the negative x. If I took the natural log of both sides, that would just say x equals negative x. Only place that happens is 0. I guess if you really wanted to, you could add x to both sides, and you would get 2x equals 0, or x equals 0. Right? So what is the x-intercept? The x-intercept is 0. So if I was going to start a graph right here, the only place I'm going to cross this x-axis is at 0. I can just guess what my y-intercept is going to be. Where am I going to cross the y-axis? It's going to be 0. But if you wanted to, you could type in f of 0. That's e to the 0 minus e to the 0 over 2, which is 0. How about that? There's the x-intercept and the y-intercept. Now, symmetry. What happens if I plug in f of negative x? Well, f of negative x is e to the negative x minus e to the x, right? Negative x over 2. Well, this looks very similar to this up here, except for that both of these terms, the sign has changed. What's that mean? That means we pull out a negative, and that would make this a negative, that a positive. I'll just go ahead and swap the order. So this term is in front. Can you see that what I have now is negative f of x? What kind of symmetry is that? That's symmetry about the origin. That means it's what we call an odd function. So whatever happens here, I'll rotate that and it would happen down here. That'll make it interesting. Okay, well, how about asymptotic behavior? The nice thing about symmetry is if I tell you what happens with an asymptote over here, we'll know over here. If I tell you vertically there's an asymptote over here, you'll know there's one over there. So end behavior, that's horizontal and slant asymptotes, and then vertical asymptotes. Let's see. Well, what would happen? The limit as x goes to infinity of e to the x minus e to the negative x over 2. Well, e to the negative x, a negative sign, remember that's a fraction, so you should think about this piece as 1 over e to the x. As e to the x gets big, this thing gets really small, so this piece goes to 0. If that disappears, what do you have? You have e to the x, that's getting pretty big. E to the 3, e to the 5, e to the 50,000, e to the 10 million, over 2. That whole thing is going to infinity. So this end is going up. Now by symmetry, that means this end is going down. You can check that actually by the limit as x goes to negative infinity if you want. Okay, so what about vertical asymptotes? That means there's no horizontal asymptote, incidentally no slope asymptote. Vertical asymptotes are only where the denominator is equal to 0 and the numerator isn't. That doesn't happen here. So there we have it. This is sort of what the ends are going to look like. Let's take the derivative and see what happens there. If I had the derivative of e to the x, and I'll go ahead and pull out my 1/2 here, just so you can see that's 1/2. Derivative of the e to the x is e to the x. Derivative of e to the negative x by the chain rule is e to the negative x times the derivative of negative x, which is -1. So I have now 1/2 e to the x plus e to the negative x. Okay? Well, this thing will never be 0, so the only critical values would be where e to the x is equal to negative e to the negative x. The problem is both of these pieces are always positive. So, what's that mean? That means there are no critical values here. This is either always increasing or always decreasing. Well, notice you plug in any value, this is positive, that's positive, that's positive. That means your entire function, I can never go down, I can never even be flat. I'm going to go through that dot, I'm always going up. Well, let's look at the second derivative. Still have a 1/2. The derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x by the chain rule times the derivative of negative x, which is now negative. Notice the second derivative is just the same as the function itself. That's sort of interesting. This does have a value that it's equal to 0. We went to a bunch of work to find that with the x-intercepts. Remember, the only value that's equal to 0 is at 0 itself. So the second derivative is 0 at 0. For values larger than 0, this is concave up. Why? Well, this would be a pretty large number. This would be a very small number. For values less than 0, you could just by the symmetry know that it was negative, or you could plug in values like e to the -10. E to the -10 is going to be very small. E to the -10, that's e to the 10th, is very big. So we have a big negative number. What's that mean? That means this is cupped up here and down here. And we have an inflection point right there. So what's the graph going to look like? The graph is going to look like that.